Much, Jerry. We'll defer any questions until the panel session, and then you can ask it. So in the interest of moving on to our next speaker, let me introduce him. His name is Dr. Jonathan Dowling. He's the Hearne Professor of Theoretical Physics at the Louisiana State University. He received his PhD from University of Colorado and has worked in Italy and Germany and for the Jet Propulsion Lab, so he too has a broad background. Now, if you can't read the title of his book in the picture in your program, it is Schrodinger's Killer App. Okay, Schrodinger's Killer App. That's what you can't see in the picture. Extended title, The Race to Build the World's First Quantum Computer. So, with that, he will describe to us some current work in quantum sensing. Thank you, Jonathan.
So I tried to follow the directions where I first upload my talk. It's good? No, I'm going to use my laptop because I just added some jokes. They told me I could just use my laptop, and I didn't know I was supposed to have jokes, so I'm going to do this. So I can tell the joke while I'm setting my thing up. So 2 theoretical physicists are on death row and have been in the same cell for 10 years. For sake of argument, we could say it would be me and Jerry Gilbert. And if you know our background, you wouldn't have to ask why we're in death row. One night, the warden comes and says, you're going to be executed tomorrow. Any last wishes? And the first theoretical physicist says, well, I've been in this cell working on a new theory for the last 10 years, and I would like to present it to all of the populace of the prison so my final last good idea doesn't die with me. And the warden says, sure, we'll set up a PowerPoint for you, and you can make some slides and present your results. And he turns to the second theoretical physicist and says, and what is your last dying wish? And the second theoretical physicist says, I would like to be taken out and shot before the other guys talk. If you've ever been in a room with theoretical physicists, I'm at the Louisiana State University. I have this new UV laser pointer. It's really, it's almost invisible. The gamma ray one is coming up next, but it's cool. You got this in China. I worked at NASA JPL. I organized the first Department of Defense workshop on quantum computing and cryptography in 1995. So I've been advising particularly the Defense Department and the intelligence communities on this for quite some time. Literally wrote the book on quantum technology when this first came out. Note the date, 2003. Now you hear this term. I should have copyrighted the title because quantum technology is used all over the place. They also use the second quantum revolution, but nobody cites my paper, so please cite it, okay? But this is an introduction to a field that didn't exist that Jared Milburn and I anticipated was coming sooner than later. So I'm going to give you just a couple of little blobs on why we're all here and what's going on that's making this interesting in the immediate and near future. This bubble for China is actually out of date. Right now, the bubble for China almost fills the entire slide. This is the amount of spending in euros, in millions of euros. So they've just invested 30 billion euros in a new quantum technology center. It'll be in either Shanghai or Hefei, where they're going to be developing quantum computing and various other things. That's an order or two of magnitude greater than what we're investing in. And they have a roadmap, and they have a plan, and they have industry and their Department of Defense and their government all integrated and working towards a common goal. Where in the US, it's much more like they have wads of $100 bills that they're throwing at the walls and seeing where it's going to stick. So hopefully, meetings like this could change that. This is something I was asked to advise people from Bloomberg News on why is the patent profile for quantum technology growing, and I said it is. So you can see it went from linear to exponential around 2012. So much of the activity now is not in government anymore in the United States. We've heard Google, D-Wave, it's industry driven. I actually have venture capitalists snapping up my PhD students who are learning foundations of quantum mechanics. When I was a PhD student, I told foundations of quantum mechanics was crackpot stuff, and I never get a job. That was a string theorist who told me that. So here's the, some of my best friends are string theorists. This is the roadmap of quantum technologies from the EU. And one of the things I'm going to talk about here, although my talk is quantum sensors, I knew Jerry Gilbert would do such a good job. I'm broadening it more out to quantum internet, which is where everybody is interested. And you can see the quantum internet is supposed to come online before the quantum computer. So why would you build an internet before you had the computers? Well, one of the ideas is to link quantum sensors, quantum synchronized clocks, and other things to the network and get an enhanced scaling similar to what we heard from Dr. Gilbert as in a quantum computer. I currently have 2 high school students modeling quantum networks, looking at networks that cannot be described by simply looking. You can make measurements locally at each of the nodes in the network and have no idea what the network is doing, where classically that is not true. Okay, so here we'll start here in the middle, foundations of quantum mechanics, you'll never get a job, okay? Then I'm going to briefly go through all of this. I'm supposed to be talking about sensors, so I'll end with that. And then the quantum internet. I don't have much slides on the quantum internet because it doesn't exist yet. But people are talking about this. All the conferences lately that I've been going to have been on quantum internet. So I'll start with the cat. And you always, I ask my high school students, do you know what Schrodinger's cat is? And they go, yeah. They all raise their hand. I go, how do you guys know what that is? Oh, Big Bang Theory, duh. So they all have some idea what is Schrodinger's cat. This was actually a paper that came out in late 1935 in August as a sort of a more popular interpretation of Einstein's EPR paper that had come out in June. And it's always delightful to have things happen like something blows up or a cat dies. But we remember there's an atomic particle. If it decays in a certain period of time, in an hour, the cat is dead. If it does not decay in that hour, the cat is alive. It has a 50-50 chance of decaying in an hour. So classically you would say, well, it's like flipping a coin, right? Heads, it's dead. Tails, it's alive. But the quantum mechanical description is that the atom is entangled with the cat, and only when you open the box and look at the cat is unreal. It's not dead and alive. It's neither dead nor alive. There's something in the box, but that's quantum unreality. You don't know exactly what it is until you make a measurement, and then it collapses with 50-50 chance to dead or alive. And I'm going to, from the 2 speakers ago, I wanted to mention people are making commercial quantum random number generators. In the early days, they did show biases, but they've gotten the bugs out of that. And NIST actually are certifying these devices as random. So that's another point, is that you could open the part of the box that contains the atom and measure if the atom is dead or alive, or decayed or not decayed. And the 2 sides of the box, one could be on Alpha Centauri and the other on Beta Pictoris, a distance of 62 light years. And quantum mechanics says that when you open the box containing the atom, it collapses to either dead or alive, and the cat, 62 light years away, instantaneously collapses to also dead and alive. And you have to believe this because it's reality, okay? This type of effect has now been demonstrated over 1,200 kilometers by the Chinese satellite program. So to go back to Professor Gilbert's story where he goes home and I'm left measuring photons, not knowing he's ducked out of the experiment, I'm going to assume we have a factory that produces entangled nickels. And we're going to do a coin toss, okay? And they ship the entangled nickels in a let's say, an egg crate. So you get 12 and I get 12. And they're numbered, nickel number 1, number 2 in the crate, okay? And then here's the weird part. whenever Jerry feels like it, home or not, he flips the first coin, records heads or tails. He could wait a day, flip the second coin, records heads or tails. I don't have to be doing this at the same time or even within the same time frame for this to work. And then I go about my business flipping the coins as well. And maybe weeks later, we compare the string of heads and tails, and they're exactly the same. Now that is weird, okay? But it's reality, and you're gonna have to accept this. This came out of Foundations of Quantum Mechanics because Einstein didn't like the fact that cats are unreal, that there's a 50-50 chance of them collapsing, and that these effects were non-local, particularly because he invented relativity. It looks like something is going faster than the speed of light, but as Dr. Gilbert said, we cannot use this to transmit information. However, we can use it to instantaneously establish a set of random numbers, which can be then used for a cryptographic key or other communication protocols. So the cat is unreal. It doesn't have an existence until you make a measurement. And this is 50-50. When I flipped the coin, I was teaching my students quantum just Monday. I'm playing hooky today. And I said, well, you know, when you flip a coin, you could in principle calculate where it would land. If I knew exactly the velocity, the acceleration of my thumb, and the friction, and how I slap my hand, I could use Newtonian laws in a supercomputer to predict heads or tails. Quantum mechanics says, no, you cannot predict that. So all of these variables, the wind velocity, friction, and so forth, we call these hidden variables. So Einstein had proposed in 1935 that we could test, well, let me rephrase this. He proposed that we could replace quantum mechanics with something like stat-mech, a hidden variable theory. We don't know what these variables are, but the coin flipping then becomes much more like just probability theory, and that's it, okay? And we get rid of unreality, and we get rid of entangled non-locality, and we get rid of this 50-50. So he didn't like this 50-50 chance God does not play dice, okay? And he particularly did not like the non-locality. So in 1935, his paper came out suggesting this at the end of his famous EPR paper, his most cited paper, over 10,000 citations, far more than his relativity papers. He suggested we could replace quantum mechanics with a hidden variable theory and then just throw out quantum mechanics. And we have something sensible. So the point is, in 1945, von Neumann, John von Neumann, at Princeton, also at Princeton at the time, proved that you could not replace quantum mechanics with a hidden variable theory. In 1955, Bohm constructed a hidden variable theory that agreed with quantum mechanics. So something was wrong with von Neumann's proof. Bell, in approximately 1965, went back and looked at the Bohm theory and the von Neumann assumptions, and in the von Neumann assumptions, there was an implicit assumption that it was local. And the whole thing about the cat, it's Alpha Centauri and Beta Taurus, it's non-local, right? So the point is you can replace quantum theory with a non-local hidden variable theory, but then you're left with weird stuff. If I have a two-slit diffraction and I use the Bohm theory, if I close one slit, an invisible, undetectable field on Alpha Centauri suddenly shifts around instantaneously. So it's just as weird as quantum mechanics, in my opinion. But quantum mechanics is easier to calculate with. Okay, so in '65, Bell said, actually, these are not two interpretations of quantum mechanics, two philosophical point of views. Can you hear me? I keep wandering away from the microphone. I will just talk in my normal speaking voice when I'm teaching a class with 70 students in it, okay? Then I can just wander around. So Bell actually constructed a generic local hidden variable theory, not the Bohm one, which was non-local, and compared it to the predictions of the quantum theory, and found out they gave different predictions in the lab. So it's not philosophy. You can test it. You can go in the lab, is Einstein right? Or is this quantum mechanics right? So the first experiments came online in 1978 and 1982. The ones that got the most marketing were these two by Clauser and Aspect. Interesting story. Clauser did the first experiment. Aspect called up the physics department and said, what happened to Clauser's old equipment? Because he left for Lawrence Berkeley. I said, oh, it's in the attic. You want it? We'll ship it to you. You pay shipping. And so Clauser was not very happy that SB used his experiment. But these are Jerry's entangled photons. It's much easier to work with photons than it is with coins and acorns. But sooner or later, we'll have something like coins and acorns. So the device emits 2 photons. It's a cesium atom in this experiment. It decays by one path or the other. If it takes path A, it emits 2 photons, one vertical and one horizontal. If it decays by... they're recording me. That's why they want me by the microphone. Okay, I'm stuck. Okay, if it goes one way, you get a horizontal and a vertical. If it goes the other way, you get a vertical and a horizontal. Since in principle you cannot tell from quantum unreality uncertainty which way it went, you get an entangled state of H, V, VH added together. This is the state unnormalized. There's no factor of root 2. So you're not allowed to do experiments with cat. People for ethical treatment of animals don't like that, but photons are fine. And the idea is you take measurements, rotate the polarization analyzers at the far ends. This was done over a distance of about 10 meters. And you make measurements, and you plug it into a formula called Bell's inequality. And it spits out a number. If that number is 2 or less, then Einstein's classical stat-mech theory is correct, and quantum mechanics is ruled out. If it's above 2, all the way up to 2 root 2, then quantum mechanics is ruled in, and Einstein is ruled out. The experiments ruled Einstein out. Clauser, a friend of mine, expected to get the Nobel Prize for proving quantum mechanics wrong. That's why he kept taking more and more and more data, because he was convinced that he was going to show quantum mechanics was wrong. No Nobel Prize. Quantum mechanics is correct. So this experiment can only be explained by non-locality, things happening here influence things happening here instantaneously. Unreality, the photon doesn't have a polarization before you measure it. And then uncertainty, when you measure it, it collapses to an H or it collapses to a V with a 50-50 probability that is unpredictable by any means. And this is reality. You have to accept this. The experiment shows this. I'm tired of arguing about this with my peers, and they suggest other explanations of this. I gave, in my class, which is quantum optics, I started out with this Bell inequality, and my physics students were flummoxed. And I took 2 engineering students, I'm calling it the quantum internet, and I asked them, well, what do you think? They go, I don't care what it means as long as it works. That's the engineering students. So we've reached that point, that's why it's quantum technology, that I no longer care what it means, it works. And we can do stuff with these very strong non-local correlations that you cannot do. Well, I hit something bad. Huh. I have bad eyes and fat fingers. All right. So here we go now, quantum computing, just a brief overview. As Dr. Gilbert mentioned, quantum computers are able to hack public key encryption. Public key encryption is used to secure most financial data and many government types of data, where Alice and Bob share a public key. It's uncrackable by a classical computer, all the classical computers on Earth, if the key is long enough. But a quantum computer can crack it in a couple of milliseconds. So this is where the scary stuff comes in. And in fact, an adversary could just be collecting all of your encrypted data, and then 10 years from now, Intel says the quantum computer, universal quantum computer, will come online in 10 years. That was their conservative estimate. So things are getting scary. They can take everything that you've ever put on the internet and decrypt it in 10 years by just storing it in a large memory. Okay? So this is Cracking the Public Key with Peter Shor. There's actually a movie in 1992. The theme of the movie was that it's hard to factor large numbers. It's hard to believe that's a thriller. But it had a mathematician at Berkeley who found a classical factoring algorithm and hid it inside of a telephone answering machine, which was then stolen by the bad guys, and the NSA comes in and says, it's quite good. But the plot is based on the inability to factor numbers. We don't think you can classically factor them quickly, but we know you can do it on a quantum computer. So when quantum computers come online, we're all using RSA public key. And what are we going to do? Okay. So the quantum computers, superconducting is the current advanced technology. I was told in 1996 when I was reviewing proposals that the superconducting people hadn't even made a single qubit and never would. They are now the advanced technology. We have semiconductor technology, superconducting. This is actually, that's a mistake. That's supposed to be ion trap there. And then there are all optical quantum computers. A repeater, as Dr. Gilbert mentioned, is nothing more than an all-optical special-purpose quantum computer that runs a particular error correction code over and over again. So if you build an optical quantum computer, you get a repeater. Quantum computer, you get a repeater for free. You're not allowed to use regular repeaters, which in fibers are simply erbium-doped amplifiers that amplify the pulses as they go down. The amplification process destroys the quantum state. It's essentially the equivalent to copying the quantum state, and it violates the Heisenberg uncertainty principle, and there's something called the no cloning theorem that says you cannot copy an unknown quantum state. So in computer science, you can't do a fan-out, make several copies of an unknown state. You destroy the state. You have to work around that. What did I say about fat fingers? Oh, there we go. I just keep hitting the blind button. So this is the number of quantum bits on superconductors as a function of time, and it's doubling every 6 months. Okay? Notice they're not counting D-wave, because D-wave is not a universal quantum computer. So these are all hoped to be eventually universal quantum computers. And so that's, remember now, the computational power goes like 2 to the n, where n is the number of qubits. So now we have a processing power that's increasing yearly by 2 to the 2 to the n. What are we going to do with that? Or what is anybody else going to do with that? Well, certainly simulations of chemical processes. Code breaking is one of them. It's sort of like asking, what are you going to do with the ENIAC in 1945? Well, I'm going to shrink it down to the size of a playing card and put it into my vest pocket and use it to play video games over the internet. And nobody would have predicted that in 1945. I believe it was Popular Mechanics when they did the study on the ENIAC. They said computers of the future might only weigh 30 tons, right? Because it weighed like 100 tons. Cell phones, okay. Quantum cryptography is the fix. We go from public key encryption to one-time pad. One-time pad was proven by Claude Shannon in 1945 to be absolutely unbreakable by any means, and it's unbreakable by a quantum computer. It's just intensive because you have to move the key around. By the old days, it was a pad with random symbols on it, and you would transcribe your message with these random symbols, and then if another person had the same pad, they would then detranslate them because they had the same random symbols. They must be random. The problem is that you must be able to distribute the pad securely, and that's the problem with the classical public key. Right now, it's only used by the CIA diplomatic corps and the nuclear launch codes. So several of us were at Air Force Nuclear Strike Command 2 months ago, and I said, well, how do you distribute the private key for the launch codes? And I'm sitting next to this general, and he says, well, we got a guy in a truck who drives to the missile silos and delivers them on 3.5-inch floppies. And everybody in the room just gasped. And I said, 3.5-inch floppies? And he said, well, they don't make the 8-inch anymore. But his response was, it's unhackable because it's a guy in a truck, right? Okay. So, but, the idea is we switch to a quantum key distribution scheme. You can use entangled photons. Here, this scheme is a BB84 scheme. It uses only quantum uncertainty and unreality. You send bits of information on your photons, horizontal or vertical, but you make different choices of which basis you're going to use, 45, minus 45, or H and V. And at the end of the day, you can, Alice and Bob share a set of random numbers they can use for a one-time pad. And any attempt by the eavesdropper to measure the photon causes the collapse of the photon's wave function, which destroys the key. So nobody gets key. So there's no way to copy the key. And with photons, you can deliver this over long distances. So this is the Chinese BB84 QKD system. It is up, running, and carrying military and financial and government information. It runs along the high-speed train line between Beijing and Shanghai. It's all fiber-based, and it's exactly the protocol on the previous slide run out. And they do have, somebody asked about the, are we going to have policies for standards and so forth? Well, we can just buy them from the Chinese now, okay? Because they have them. I mean, there are people sitting in booths. This is all running a very large network. Now, this is a hero experiment because we don't have the quantum repeaters. So each of these red blobs is a secure node. So how do I get farther if I don't have a repeater? Well, until the repeater comes online, we do it by satellite. So this is the satellite not making any funny noises. It distributed random key, as Dr. Gilbert showed, to Beijing, and then the other half of the random key to Vienna in the telescope in Graz. And so they did a one-time pad secure video conference using this key. Now this satellite is a test bed for doing things like this. The next Chinese proposal in 3-4 years is to have a network of nano satellites which do nothing but distribute random key from space. I would not use that key because the satellites know everything. So that's the state of that. Now, yeah, someone asked about the random number generator. So people are making these in China. The VB84, as Dr. Gilbert mentioned, requires random numbers. They're using quantum random number generators. And we're building our own here and certifying that they're random. The problem is it's hard to tell if something's random or not. Because in any long string of random numbers, you're going to get an infinitely long string of in pi, you'll get a lot of 9 sooner or later. All right, quantum sensing and imaging. What is my time?
Well, we should wrap it up soon.
Yeah, okay, I'm in the last bubble. So good, Dr. Gilbert already talked about this. The sensing part is basically, we call it, if you entangle particles together, light beams, two things. For light, you can beat the Rayleigh diffraction limit, as he mentioned. And you can also beat the shot noise or the quantum limit, as he mentioned. And you don't have to just do it with light. Entangling atoms gives you an improvement in gyroscopes. This is precision inertial navigation at a level where we can operate submarines in a GPS-denied environment. And you can do a photonic version of this as well. Quantum magnetometers is something that I've worked on, funded by the Air Force. One of the interesting new ideas that we're working on is networks of clocks in space. This is a paper by a group from Harvard where they showed that you get an advantage, this 1 over square root of n versus 1 over n in the accuracy of the clocks from having the clocks entangled. So this is a UK quantum sensor roadmap and their imaging roadmap. I'd show you the US one. We don't have one. I'd show you the Chinese one. They won't give me the slides. So the quantum internet, well, I'm going to give you just one last fun thing. So everybody has heard of quantum teleportation, and this was just thought to be something cute. Whenever you design a computer architecture or network architecture, one of the key questions is how do you move data around quickly? And the answer is, for a quantum network or a quantum computer, you teleport. Now, you might laugh, nothing to do with Star Trek, but it doesn't violate the no cloning theorem. You make a measurement here, a state here instantaneously appears over here. You send 2 bits of classical information and you can reconstruct the state. So almost all of the effort is in this classical channel, which could be smoke signals or your cell phone or something else. And so that's how you move quantum data around the internet. So there were 2 experiments, there were 3 experiments on the Chinese satellite. The entanglement distribution, testing whether Einstein is right or quantum is right, over 1,200 kilometers. They've done the VB84 QKD over 4,000 kilometers, and this is a teleportation up to 1,400 kilometers. They teleport an unknown quantum state up to the satellite. So the teleportation is a primitive for any network for moving data around. So this is just not Star Trek stuff. This is how you're going to move data in a large quantum network. These are my 2 high school students, and Mary Catherine and Deepti, that were working on with me on the summer. We're designing new quantum networks. They don't know much about what quantum is, but they just care that it works. And so they're running computer codes on different graphs with different models. Finally, the repeaters and memories are the last thing. We don't have a repeater. If we did, a good one, We wouldn't need the satellites. If we had, we could just run everything out on fiber and the satellite wouldn't be required. But many of you remember in the old days when you made long distance calls, we didn't have fibers. It would go up to a satellite and there would be a weird delay when you spoke. You don't hear that anymore because everything's on fiber. So eventually this will come along, and this is going to be a disruptive technology. So I will quote my own book. Okay, the quantum repeater is a special purpose optical quantum computer. Runs an error correction. The quantum internet is photons, short-circuiting development of optical quantum information processors in the United States. We had a big program that IARPA killed in 2010. Had they not done that, we were 9 months away from a launch, a rocket launch to test BB-84 from outer space, and it was killed by IARPA with only 30 days warning. A large waste of money. We'd have been ahead of the Chinese, but we're not. Okay, but anyway, so the United States, that lack of a program in the United States means the future quantum internet will have made in China stamped all over it. Now, I wrote those words in 2012, and people laughed. Now they're not laughing. And if you email me, I'll send you the PDF of the book for free. I'm already working on my new one, Schrodinger's Web, The Race to Build the Quantum Internet. So this one I'm not making any money off anymore. Okay, that's it.